Hello, welcome back to another exciting episode in chemistry. Today we will begin with the gas laws, or the chapter on the gases, which I have divided into 4 episodes or 4 modules. We will start today with gases 1, as you see on the screen, and we will discuss a few topics that will help us explain the gas laws and the state functions. We all have seen or heard about the airships that definitely involve gases. Of course, you know where the gases are, but this is a wonderful example of the airships and blimps that used to travel around the globe, and now they're mainly used for advertising purposes. And they use the filler gas of hydrogen or helium. And I should rather say hydrogen is not used anymore because of its combustionability. We all remember the Hindenburg episode. The topics that we will discuss today are listed here, so I will read through them quickly. The kinetic molecular theory, which is so important in describing the physical states of the physical states, the solid, liquid, and gaseous state. They are best applied to the gaseous state because of the concept of the ideal gas. And we will discuss that because there's a difference between the fictitious ideal gas and the real gas that we observe in our environment. But some gases do behave closely to this ideal gas concept, so we can sort of approximate this ideal concept. The state functions that are involved in describing the physical state of the gas, meaning what type of pressure does it have, what volume does it have at certain temperatures, or what temperature is involved with the other 2 state functions. So they correlate in a wonderful fashion that we will see reflected in the so-called gas laws, which we will discover and discuss next time. But today we will just describe their meaning, how they are understood according to the concepts of the kinetic molecular theory. We will discuss their meaning accordingly, and also the forms of measurements that allow us to give some numerical value to these state functions. And of course, last not least, the units involved, because every measurement is a dimension. We have a coefficient, a numerical figure, and the unit. Together we call that a dimension, as you remember from earlier work. So the methods and devices of the measurements of pressure, temperature, and volume. And of course, we have to discuss the physical concept of kinetic and potential energy, which are constantly interrelated. The kinetic molecular theory is still a theory and not a law, because it doesn't function for all kinds of situations, so that's why we still call it a theory. But the theory means that all particles, especially the gas particles, are in constant motion. Kinetics comes from the Greek word kinesis, meaning movement, action. So if you look at this bottle, and we have these 5 little spheres in here. They represent gas particles, and they're in constant agitation, meaning they have a high degree of kinetic energy and constantly bump into the container walls. And if the temperature gets higher, they will be more agitated. If it gets lower, they're a little bit more sluggish. So you see already how these things interrelate. So they all have a certain kinetic energy, activity. The kinetic energy is, by the way, the mass times the velocity square of the individual gas particles, be they atoms or molecules. So E kin is mass times velocity square. So all these state functions can be wonderfully understood by utilizing the kinetic molecular theory. What are the state functions? The state functions describe the state of a given material. They determine the actual physical state. Is it liquid, solid, or gas? Or if we're dealing with a gas all the time, what kind of conditions are involved, and what is the resulting pressure, volume, and temperature, the energy state of the gas. So it might not be apparent to you what the actual physical state is of the gas, but we can certainly get close to it in numerical values. Now you see when a gas is liquefied, you see a liquid. That's obvious. But if a gas has a higher kinetic energy or not, you won't see it. Only on a hot day, of course, then the gas particles move faster and you feel it on the surface of your skin, etc. For solids and liquids, that could mean different crystal lattice structures or different mobility of a liquid, different densities, etc. For gases, the physical state just involves a combination of pressure, temperature, and volume. Later on, also the number of particles plays a role. We call that the mole content, but we'll get to that later. So the meaning of P, V, and T: pressure is determined by the number and intensity of the collisions with a container wall. So if there wouldn't be this container, we couldn't talk about pressure. Pressure needs some form of resistance. And the higher the temperature, as I've already shown, the more agitated the molecules will be. And you can see if we have a higher temperature, the pitch of the collisions, or what we hear audibly, will be a higher tone. At low temperatures, the gases move a little slower. And the more particles I have in this bottle, the higher the pressure will be as well, because we have, per given area, more collisions. So you see that is already very suitable in explaining pressure. And also, you can see already how temperature and pressure are related. As you can already guess, they're directly related. The higher the temperature, the more agitated the particles are, the more effective the collisions are with the container wall. So there seems to be a direct relationship. Volume also relates to the conditions, external conditions, although here I have the external condition of a confined space. So the volume is confined. So the particles have no more space to move about in. But if I open the lid, the gas particles can come out, and guess where they're going? They're going into space. So then there's no pressure. Maybe they will bump into the walls of the studio. But if somebody opens the door, then eventually, by virtue of their chaotic movement, will find the exit doors and move into space. So we already related pressure with temperature and concentration, meaning the number of particles. If you have more particles to collide with the wall, more collisions per area, meaning higher pressure. Here's a question that you can think of at home without any knowledge of the gas laws. You can already figure that out just by instincts. Now let's define the physical definition of pressure, and we will show that here in our drawing. And you see that the definition of pressure in a physical sense is force per area. Now you've all stepped maybe on a thumbtack or on a nail. Oh goodness, that's pretty painful. Well, why is it painful? Because the area of the thumbtack, the tip of the thumbtack, is very, very minute, very small. But your weight, if you're heavy, will be the force exerted on that small area, and therefore you will get a bigger neurological response, and you will exclaim, ouch, more defined. So therefore, we can say that pressure is the weight of the person over the tip of the thumbtack. So let's say the person weighs, we'll move it over a little bit here. Let's say the person weighs 110 pounds. That's a good honest weight, average weight. And the thumbtack tip is 0.01 square inches. then the pressure exerted on the surface of the skin is practically 11,000 psi. And that's the unit you're probably familiar with. That's pressure or pounds per square inch. Now that is not an SI unit. We have to stick, when we're dealing with sciences, to the international set of allowed units and measures that is guided by the SI system, as you well know. So we can leave this and see how is pressure measured. And we distinguish here between measuring outside pressure and something that is in a given container. Now, external pressure is our atmospheric pressure, for instance, and that can be measured by the barometer. Baros means pressure in Greek. And a wonderful liquid that is used is mercury, because it's so flexible and has a very even expansion coefficient. It's very dense, so that we can use it in a confined space. We could use it with water too, but mercury is the ideal liquid. It's the only liquid metal under normal conditions. So we have here a little container with mercury and an inverted tube that is evacuated, submerged into the liquid mercury. The outside gas particles from our atmosphere will constantly collide with the surface of the mercury, and mercury tries to evade the pressure, of course, like any material would. You don't like to be bumped into or pushed around, so you try to get out of the way. And so the mercury atoms will also try to get out of the way. And where can they go? They can crawl up into that inverted evacuated tube, because the vacuum means there is no pressure. So you take the route of least resistance, and the mercury atoms will creep up. So that means if you graduate this column, then you can actually give a value to that increase of pressure. That's why we use the millimeter scale. For instance, just like here in this thermometer, we have a millimeter scale. So we call the pressure also, the height directly relates to the millimeter mercury. So barometer we find in our environment today. We will see a real barometer in one of our labs soon, so you can see it in real life, so to speak. Some of you have barometers at home to measure the weather changes, so high pressure and low pressure areas. You know how that relates to good or bad weather. So the height of the column is measured in millimeter mercury. And 760 millimeter mercury is the same as 760 torrs. Torr, coming from the famous scientist who invented the barometer, Torricelli, of Italy about 300 years ago. And 760 millimeter mercury, or 760 torrs, equals to 1 atmosphere. So that's practically our normal pressure in our environment. Of course, we have some higher pressure conditions, some lower pressure. In California, we often have 730 to 40 millimeter. In high altitudes, it's lower. In low altitudes, it's higher. We know about weather conditions. So that is our barometer. Let's look at our manometer. Manometer is a device which also is based on mercury. And we'll move it up here. So that's called a closed-end manometer, and it's in a U-shaped tube. We also have one side of the tube evacuated, and the other end of the tube is connected to whatever we want to measure, like this bottle here. So we can measure it. We can use the manometer to measure the pressure of a given container, like a gas bottle. Or when we want to evacuate a system, we can also control our progress. Now, the difference between the two columns means a higher millimeter mercury distance, and therefore higher pressure. And if the two columns are equal, then we can say the vacuum is equal to the pressure that is in the system, and therefore the difference is 0, meaning we have successfully evacuated the container. It's very difficult to get an absolute vacuum, but one can get close enough. Now let's get back to the units of pressure. I already mentioned that 1 atmosphere is 760 millimeter mercury. 1 torr is 1 millimeter mercury. So 760 millimeter mercury are equal to 760 torrs. And 1 atmosphere is measured in SI units, 101,325 Pascal, also in honor of a famous scientist that was involved in this type of research. And a Pascal translates into Newton, which is the SI unit for force, over square meters, which is an SI unit for distance. And therefore, you see how Pascal is defined by other SI units as well. Now, let's go back to the physical chemical definition of gas pressure according to the collision theory. I demonstrated that already in the bottle, right? That the gas particles are in constant motion. Here's a little sketch of a compressed gas tank, and the little dots represent the gas molecules. The little arrows represent their velocity vectors, meaning that's the direction they're moving, and the length of the arrow represents the intensity of their, or the speed of their movement, or the velocity. So all gas particles are in constant motion. They collide with the container walls. And very, very rarely do they ever collide with each other. Why? Because the ideal gas concept means that the gas molecule is practically of 0 mass, has very high kinetic energy, and no intermolecular forces at all. So you see the gas particles push the mercury atoms out of the way. The mercury atoms receive the momentum of the of the gas particles, so that they start moving too. Remember, a liquid and a solid also involves movement of particles. So you see the momentum is translated through the material, and the gas or the mercury atoms will try to go into the vacuum. Therefore, the bigger the difference of the two U-shaped columns, the bigger the pressure is involved. So the kinetic energy is directly related to temperature. So we can say that thermal energy is actually kinetic energy of particle movement. So we have understood pressure pretty well. Let's now go to volume. And volume is very easily determined because it's nothing else but the actual container. The gases have the unusual property of filling out every niche and cranny of the container provided to them. So they will, because of their constant zigzag chaotic motion, they find every little niche of a given space. So you can see here in this bottle, the volume is 5 liters as an example. And let's look at heat again and temperature. I'll get back to, or let's just move this up and we can go to the temperature. The meaning of the temperature according to the molecular theory. We can now understand with the help of the molecular theory that heat flows always from a hot zone to a cold zone. Never goes in the reverse. Why? Because the velocity vectors of the hot particles will bump into the cold particles and accelerate them. Just like when you're in a subway or in a train or someplace and somebody bumps into you, you're going to be also accelerated in your kinetic condition. So the sluggish molecules will be excited by the fast ones, And we know that with rise in temperature, matter tends to expand because they try to get out of the way. So we already see that the contents of the mercury thermometer, which is used also as, you see, mercury is also used not only in measurement of pressure, but also in the measurement of temperature. And the kinetic molecular theory has the same profound effect on the properties of mercury. The fast molecules of the environment bump into the mercury through the glass. The glass practically translates the momentum onto the mercury particles so that they internally will move up into the evacuated space. And you see here a real thermometer and the tip being the mercury. And there's a little, tiny little tube in there which is called a mercury thread. So heat, let's look at heat. Heat is thermal energy, and as I already mentioned, directly related to temperature. And we already understood that the higher the temperature, the outside temperature, the higher the speed of the particles. So this is, let's say, a little Bunsen burner that speeds up the molecules in the bottle. So the kinetic energy is higher at high temperatures than at low temperatures. So you see thermal energy is related to kinetic energy and is related to the speed of the molecules. The unit of the heat, or of heat in general, used to be the calorie. You know that still when you eat things, how many calories it has. But the SI unit is the joule. And the conversion would be 1 calorie is 4.184 joules. So you see, what we said before is that matter expands, particularly mercury, and mercury is so good in using as a thermometer material because of its regular expansion coefficient. Now, what are the units for temperature? So temperature, in a way, is a measurement of heat. It's not the same as heat, but because of the kinetic molecular theory, the material that is used to measure temperature expands, and if we use a gradation of its expansion, meaning putting little margins here that are the increments of temperature measurement, then we can say certain environmental conditions mean that we have a certain temperature. What are the units? The SI unit is the Kelvin. It's not using the degree sign, by the way. We will learn where the Kelvin comes from next time when we talk about the gas laws. The Europeans usually use centigrade, and the Americans and the British use the Fahrenheit. But Fahrenheit was a German fellow who started that temperature scale when we want to look at the history of measurement of temperature. There are certain conversion formulas that allow us to go from one unit to another. There used to be also a French one called Reaumur, which I will not include here because it's hardly used anymore. Now we are practically at the end of our session, but I would like to show you something interesting having to deal with random movement of the gas particles, temperature, and its so-called free energy. Notice what I said before, that molecules of the gas phase hardly collide with each other. They just bump into the container. Here, for instance, we have a small vessel and here a bigger bottle. This is 1 liter, this is 10 liter. And what does that mean here? We have a more confined space in which a certain amount of particles move about in. And here we have a bigger space, so that means the molecules have more room to move about in. Therefore, the probability to find a particular molecule at a certain space is higher. So you could say with increase of volume, we have a higher entropy. But the pressure is lower, as we learned, because there are less particles bumping into the container wall. So therefore, the pressure is lower. So at low pressure, we have a higher entropy, and at a higher volume, we have a higher entropy. Now, I'm saying entropy. What does that mean? Entropy is the degree of disorder, the degree of chaos, and the highest probability of finding a particular particle at a given area of the container. So that's an interesting relationship, but we will learn more about that when you go to higher chemistry courses. But before we end our episode today, I have some models that I want to show you of some of the gases that we deal with. Now, the molecules that come closest to the ideal concept are those that are relatively small in size and also have a low mass, which we call, of course, here the molar mass, grams per mole, or relative atomic weight, which we define in AMU units. So this is hydrogen, which has the molar mass of 2. And if we take this orange little sphere, we can consider that a helium atom. So you see it's very light. It has the molar mass of 4. Here we have oxygen, which is 2 oxygens bound together by virtue of a double bond. And it's 32 grams per mole, so it's quite a bit heavy already. Do you think which one would move faster at a given temperature? Well, the lighter one will move faster. Methane, carbon and 4 hydrogens. And carbon dioxide, pretty heavy. It's 44 grams per mole, so that would be the heaviest guy and the slowest one to move about at a given temperature. And last not least, we have nitrogen. Triple bond, but now it's time to go, and we will learn about the gas laws next time. Goodbye.